In the second part of the video on quantum gates, I will be explaining few more quantum gates. And in this video, first let us start with the second quantum gate, that is the Pauli Y gate. The working of this gate is similar to the X gate, like it takes the single input and it transforms the single input to the single bit output. And like the X gate, it is also a unitary and Hermitian matrix. But the working of this Y gate, Pauli Y gate, is like this. If the input is the qubit 0, it transforms that input into I times qubit 1. And if the input is the qubit 1, the output is minus I times qubit 0. If the input is a superimposed state like alpha times gate 0 plus beta times gate 1, when we apply this input to the Y gate, the output what we will get is, because we are applying over the Y operator over uh, linear addition, and we get alpha times Y gate 0 plus beta times Y gate 1. And when we apply Y over the gate 0, what we will get is the I times gate 1. And when we apply Y over to the gate 1, we will get minus I times I0. So that's why the superimposed state is converted into, in which coefficients of alpha and beta are interchanged, and the term that we will get is alpha times I times gate 1 minus beta I times gate 0. So this is the working of the Y gate. The matrix for the Y gate is again a 2 by 2 matrix, and the input column is 0 I. The first column of this matrix is 0 I, and the second column of this matrix is minus I and 0. So let us try to apply this matrix and see the verify the result on when we apply Y on the input gate 0. This is the Y matrix for uh, Pauli Y gate, and this is the vector representation of gate 0. If we multiply these two matrices by first multiplying this row, first row with the first column, what we will get is the 0 times 1 plus minus I times 0, and which is nothing but the 0. And if we multiply the second vector with the column, this column vector, we will get I multiplied by 1 plus 0 multiplied by 0, which is equal to I, and which is nothing but equal to the I times gate 1, because the I is present at the 1 position. So that will become the coefficient of gate 1. So this is the output for when we apply uh, Y gate on the input gate 0. So in this way, you can also verify other inputs like gate 1 and a superimposed input like alpha times gate 0 plus beta times gate 1. So this is the working of the Y gate. Similarly, there is another gate, we call it as the Pauli Z gate, and The symbol for the Pauli Z gate is like this, which takes one input and one converts that input into the output. It is also a unitary and Hermitian matrix. The matrix of the Pauli Z gate is the first column is 1 0 and the second column is 0 minus 1. The size of the Pauli Z gate is again 2 by 2 matrix. The working of this Pauli Z gate is like this. If the input is the gate 0, then output is also the gate 0. It does not get transformed. Then if the input is the gate 1, the output is the minus gate 1. And we in the x and y gate, the working of the on the superimposed state can be explained by applying z over the linear terms of alpha plus beta 1, which becomes alpha times z, apply z to the kate 0, and beta times and apply z to the kate 1, which will become alpha times kate 0 minus beta times gate 1. So this is the working when we apply Z gate on the superimposed state. Let us verify one input uh, when we apply by matrix multiplication. When we apply gate 1 to the input as a input to the Z gate, let us replace Z by its equivalent matrix. This is the Z matrix, and this is the Kate representation, vector representation of the Kate 1. And let us do the multiplication of these two matrices. 1 0 is the first row, and this is the column. 1 multiplied by 0 becomes 0, and 0 multiplied by 1 becomes 0. So these are the two terms, and the addition of these terms is the 0. Now let us apply second row, 0 minus 1, and do the multiplication. 0 comma 0 and minus 1 comma minus 1 into 1, which will become minus 1. So this is the vector representation of minus kate 1, because the minus 1 is present at the 1 position. So this is the working of the Pauli Z gate. Like that, there are additional gates are also there, which we call it as the yes gate. Yes gate is a single input, single output gate like our previous X and Y and Z gate. It takes one input and one output. It is a unitary matrix, but not a Hermitian matrix. So the matrix of the S gate is the first column is 1 0 and the second column is 0 I, and the size of the matrix is 2 by 2. And the working is like this: if the input is the 0, gate 0, the output is also gate 0, like our previous Z gate. And if the input is the 1, the output is I times gate 1. And if it is the superimposed state, we are applying S over the linear sum of alpha plus beta, and we will get into apply S on the gate 0 and apply S on the gate 1. We will get alpha times gate 0 plus I times beta gate 1. So this is the super application of the superimposed state as an input to the yes gate. Let us verify one again, one input by doing matrix multiplication for the yes gate. So if the input is the qubit 1, this is the yes matrix for yes gate, and this is the gate, this is the vector representation of gate 1. And do the matrix multiplication first by applying the first row. 1 multiplied by 0 becomes 0, 0 multiplied by 1 becomes 0. Then do the second row multiplication. 0 multiplied by 0 becomes 0, and I times 1 becomes I. So this is simplified like this 0 I, and this is the vector representation of I times gate 1. So the next input single input gate is the T gate. Like earlier gate, T gate is a unitary matrix but not the Hermitian matrix. It again takes one input and converts that input into the output. The working of the T gate is like this. If the input is the gate 0 or the qubit 0, the output remains the same, gate 0. If the input is the gate 1, it is shifted by e to the power of I pi by 4 times gate 1. And if the input is the superimposed state, apply T gate over the both terms T0, both terms ket 0 and the ket 1. And if the input is the ket 0 for to the T gate, it does not change, but the input is the qubit 1, it is shifted by a degree e to the power of pi by 4. So the matrix for this T gate is like this. The first column is 1 0, and the second column is e to the power of pi by 4. The size of the matrix is 2 by 2. Let us do the multiplication of let us verify the results by doing matrix multiplication. If the input is the gate 1, so to the T gate, let us replace T by its equivalent matrix and gate 1 by its vector representation. So this is the matrix for T gate and this is the matrix for gate 1. If we do the matrix multiplication of these two matrices, what we will get? 1 0 times 0 1. So 1 0 is 0 and 0 1 0. So the first term becomes 0, then second 0 0 multiplied by 0 comes 0, and e to the power of pi by 4 times 1 becomes e to the pi by 4. So this is the resultant matrix when we apply T to gate 1. So the output is e to the power of pi by 4 times gate 1. So these are some of the additional gates. Thank you.